Hi everyone, I just wanted to give you guys some help with a problem set, and so I'm going to show you guys how to solve the answers. At any time you can stop in the video if you want to try for yourself. This is the first problem, and if you take a look at the problem, you see that very clearly this is a titration problem. So you have some sort of acid here that you use for titration, and with this acid you titrate a sample of NaOH. And our goal is to get the concentration and molarity of the NaOH. So how do I do this? Well, first of all, like every chemical problem, you want to set up a balanced chemical equation for this direct titration. Well, in this case, sulfuric acid is a diprotic acid, so you need 2 sodium hydroxide to neutralize the sulfuric acid. Now, I like to collect terms that I know below the terms in the balanced chemical equation, so I know I needed 45.7 milliliters of 0.5 molar H2SO4, and I had a 20 milliliter sample of NaOH. Now, by definition, the molarity of NaOH is equal to the moles of NaOH divided by the volume of NaOH. Now, the volume of NaOH I already have. The question is, how do I get the moles of NaOH? Well, in order to do this, so how do I get these moles of NaOH? In order to do this, I'm going to use this fact that I have the moles to each endpoint of the acid. And so what I'm going to do is I'm going to calculate the moles of sulfuric acid, which is basically equal to 45.7 divided by 1000 liters times the molarity. So, and if I do this, I get 0.02285 mole. Great, so these are the moles of sulfuric acid. Now I need the moles of sodium hydroxide. So the moles of sodium hydroxide is equal to the moles of sulfuric acid times, well, now I need the mole-mole ratio. So in order to go from sulfuric acid to sodium hydroxide, I need to divide by 1 and multiply by 2, which in this case becomes 0.0457 mole. So now that I have calculated the moles of sodium hydroxide, it's just a plug and chug problem. So pretty much my molarity is equal to 0.0457 mole divided by 0.020 liters. And if you calculate this, this should give you 2.285 molar, which is not in the range to answer the question. In this problem, we're given 2 grams of sample, and the sample contains acetic acid, and it also contains some water, so it's contaminated. And we want to know how much acetic acid is in the sample. Well, in order to do so, we're dissolving this in 100 milliliters of water, and then we're taking 20 milliliters of this and we're taking 20 milliliters of this and we're titrating it. Well, how much should we titrate with? We titrate with NaOH, and what do we know about the NaOH? Well, we know it's 0.218 molar, the concentration, and we know the volume, 28.25 milliliters. Well, that's great because the NaOH only reacts with the acetic acid according to this balanced chemical equation here. Now, the important thing is that this is a 1-to-1 mole-mole ratio, and if you titrate to endpoint, then you can determine the moles of the acetic acid from the moles of sodium hydroxide. Let me write the information that we have down here below the equation. Now, this part here allows me to get the moles of NaOH. And by now you should know molarity times volume gives me mole, and you should be able to show that the moles for this should be about 6.16 times 10 to the minus 3. Now it should be clear that this is the same moles as the moles of acetic acid in 20 milliliters. So this is the same moles of acetic acid. Why? Mole-mole ratio 1:1 in 20 milliliters. Well, we are not looking for how much acid there is in 20 milliliters. We want to know how much acid there is in 100 milliliters because we dissolved our original sample in 20 milliliters. So I need to scale this up. How do I scale this up? To find the acetic acid in 100 milliliters, I'm going to do 100 over 20 times 6.16 times 10 to the minus 3 moles. And that gives me 0.0308 moles of acetic acid in 100 milliliters. Great. Now I got the moles of acetic acid in 100 milliliters, and as a chemist, when you see moles, you automatically see grams. How? Molar mass. So mass times molar mass gives me 0.0308 moles times 60.05 grams per mole, which is equal to 1.85 grams of acetic acid. Well, this is great because this number here is the mass of acetic acid in the sample. And the original sample weighed 2 grams. So in order to calculate the mass percent, I'm going to squeeze this in here, of acetic acid, that's equal to 1.85 grams, the mass of acetic acid, divided by the mass of the sample, times 100. And if you multiply this out, this should be 92.5% approximately. This problem here is an interesting problem, and if you read carefully through this problem, you should recognize, hey, this is an indirect titration. Well, what do? We take a flask, and in this flask, we're going to put 25 milliliter of ammonia. Then we're going to react this ammonia with HCl. How much? Well, if you look at the problem, 50 milliliters, 0.1 moles per liter or molar of HCl. Now, this is the total acid added. And we can calculate the moles. And in this case, it's just 5 times 10 to the minus 3 moles. Great. Once I have the moles of total acid added, the acid, the HCl, will react with the NH3 according to a very simple reaction. In fact, NH3 react with HCl to form ammonium chloride. Now, the ammonium chloride that is formed used up all of the ammonia. So this is the limiting reactant, and this has some excess HCl left. So basically you're leaving a solution which has HCl protons floating around. What are you going to do with this solution? Well, we're going to add sodium carbonate. Why? Because 2H plus CO3 2 minus forms CO2 plus H2O. So we know we're going to form some bubbles, and we're going to use up the excess acid. So here we have a titration. Well, from the carbonate that we use, we can calculate how much acid there was left over. From the leftover acid and the total acid, we can calculate how much acid reacted with the NH3. So let's do this calculation. The mole of sodium carbonate is equal to the molarity times volume, which in this case is equal to 1.075 times 10 to the minus 3 moles. Of course, I used this information up here to calculate this number. Now, in order to calculate the moles of acid, there's a 2-to-1 factor. So the moles of HCl is equal to twice this, which will be 2.150 times 10 to the minus 3 moles. Now, this here is the excess. And this here is the total. Now, how do we get the acid HCl that reacted with the NH3? Well, that is very easy. The moles of HCl that reacted is equal to the total minus the excess, which in this case is equal to 0.00285 moles. Well, if that's the moles of HCl that reacted with NH3, then you can calculate the moles of NH3 because it's 1-to-1. Now, the problem asks for the molarity of NH3, and that is equal to the moles of NH3 divided by the volume of NH3, and the volume of NH3, of course, is 25 milliliters. So that is equal to 0.00285 moles divided by 0.025 liters, and that gives you a molarity of 0.114 molar. In this problem here, we're supposed to determine the molecular formula, and we're given some interesting information. In the first experiment, a sample is burned, and if you look at it closely, this is a combustion analysis problem. So go back to your lecture notes to make sure you understand how to do a combustion analysis problem, and it will give me the empirical formula. So experiment 1 will provide me with the empirical formula. Now, if you think about it, in order to go from empirical formula to molecular formula, you need the factor. And remember, this factor depends on the molar mass of the empirical formula and the molar mass of the molecular formula. So we need to somehow determine the molar mass of the molecular formula, and I can already imagine that this second experiment here has something to do with going from the empirical formula to the molecular formula. So let's take a look in detail. What we first want to do is determine the empirical formula. And usually what I do is I write down a kind of unbalanced chemical equation. I put my masses that are given there, and the sample was 1 gram. And then I need to use this information to determine the grams of carbon, hydrogen, and oxygen. Why? Because I want to have a table which has carbon, hydrogen, oxygen, which has the grams, the moles, and the mole fraction. Well, in this case, 0.223 divided by 44, the molar mass of CO2 times 12, and you should see your lecture notes for this, gives me the grams of carbon. So if I do this calculation, I get 0.608 grams of carbon. I can do a similar thing for the grams of hydrogen. Remember, divide by 18 the molar mass of water times 2 times 1, molar mass of hydrogen. There's 2 hydrogens of water. So from the 0.39 grams, I can get 0.043 grams of hydrogen. Now remember, grams carbon plus grams hydrogen plus grams oxygen is equal to the mass of the sample. And my sample weighs 1 gram, so if I subtract the grams of carbon and hydrogen, I should get a mass of oxygen of about 0.35 grams. Great. So now that we have the 3 masses, you convert them to mole. This should be straightforward using the molar mass from the periodic table. I'm going to omit the units, it's all in moles. And then I look at the 3 numbers and ask myself, which one is the smallest number? Well, very clearly the moles of oxygen. So I'm going to divide each of the 3 numbers by 0.022. That gives me a 1 here, it gives me a 2 over here, and it gives me 2.33 up here. Now, in order to get the empirical formula, I multiply this by 3, and I get an empirical formula of C7H6O3, and a molecular weight of the empirical formula of 138.12 grams per mole. Now, how do I determine the molar mass of the molecular formula? Well, by definition, the molar mass of the molecular formula is equal to the mass of the molecular formula divided by the moles of a sample of the molecular formula. Now, I need somehow a mass of a sample, and I need to determine the moles of the sample. Well, in this case, here's the mass, which is right here, and I'm looking for the moles, and in order to find the moles, I see that there's a titration here. Now, it should be very simple for us to see that it is a 1-to-1 mole-mole ratio between the base and the acid, and it should be very simple and straightforward to calculate the moles of the molecular formula, and that should just be 0.07240 liters times 0.1 molar times 1/1 for the mole ratio, and that should give me 0.007240 moles. Plugging in 2 grams, I get the molecular formula, the molar mass of the molecular formula, which gives me 276.24 grams per mole. Now let's compare the molar mass of the molecular formula to the molar mass of the empirical formula, and it should be clear that the factor is 2. So my molecular formula should be twice my empirical formula, so that should be C14H12O6. In this problem here, I have a mixture, 1 gram of benzoic and gallic acid, and I dissolve this mixture in water, and when I do, I get protons because both benzoic acid and gallic acid are protons. And then what I do with the sample, I add hydroxides to neutralize, so I titrate with NaOH. Now, in order to figure out how much benzoic acid and how much gallic acid I have in the sample, this is actually quite a complicated problem because the base NaOH will react with both the benzoic acid and the gallic acid. So this NaOH the hydroxides will react with the H plus you get from benzoic acid and gallic acid, and the base will provide the hydroxides. So how do we solve this problem mathematically? Well, let's take a look. 1 gram sample is equal to the mass of benzoic acid plus mass of gallic acid. And just to make it simple, I'm going to use x and y here. So 1 is equal to x plus y. This is my first equation, but 2 unknowns. And in order to solve it, I need another equation. Well, where does the other equation come from? It comes from the titration. Well, what happens in the titration? Well, in the titration, at equivalence point, moles of OH minus is equal to moles of H plus. The moles of hydroxide, of course, are obtained from NaOH, so we just take 0.5 molar and multiply this by the volume we needed, which in this case was 0.0147 liters. Now, if you do, that gives you the moles of hydroxide, which is 0.007355 mole. Now, the moles of H plus, well, where do the H plus come from? They come from 2 components. They come from the moles of H plus that come from gallic acid and the moles of H plus that come from benzoic acid. So far so good, but I don't know what the moles are, and these are additional 2 unknowns, so now I would have 4 unknowns, which is not useful. However, in chemistry, we know there's a relationship between moles and the mass. Now, to utilize this relationship, we first need to recognize that for every 1 gallic acid, I get 1 proton, because it's monoprotic. So this is equal to the moles of gallic acid plus, and the same is true for the benzoic acid, the moles of benzoic acid. Now to convert the moles into mass, we use the molar mass. So this is equal to Y over 170, the molar mass is given, plus X over 122. Remember, mass divided by molar mass gives me moles. So now I have an equation here that also contains X and Y. This is equation 2. Now, given equation 1 and 2, in order to solve those, there's many ways. One of them you learned in math, which is substitution. So, for example, you can sub equation 1 into equation 2, solve for X or Y, and once you solve for X or Y, you should get the mass percent of 36.6% and 36.4%. And I leave it up to you to do the math, but if you are uncomfortable with the math, come by our office hours and I show you how to get a solution by substitution. Okay?